Hello everyone. Let us continue with what we have been doing since last class. Last class we had one demonstration of three moment equation, and then that demonstration was through a continuous beam, three span continuous beam. Okay, and they are subjected to some external loading, and we determine what was the bending moment, what was the bending moment at different supports, and then what will be the corresponding bending moment diagram. Okay, and this was the problem we considered yesterday, and this is the deflector shape of the beam. Now, in this example, the flexural rigidity of all these span A, B, B, C and C, D, all these flexural rigidities were considered as constant. Okay. Now, those flexural rigidity, but in real life structure, that flexural rigidity for different members, we may have different values. Now, we will see then if they have different values, then for the same problem, same beam, same length and subjected to same loading conditions, how they behave differently, different span behave differently. Okay. Now, this was the deflector shape of the beam, where all the flexural rigidity were EI. Now, suppose now the flexural rigidity is different for different span. So, for member AB it is 2 EI and member it is EI, and for member CD it is 0.5. Means what exactly we are doing? We are making member AB more stiff, member BC as it is, and the member CD less stiff, more flexible. Okay, so we reduced the stiffness of member member CD by half of the previous stiffness, and we increased the stiffness of member AB by 2. Okay. Now, let us see what happens for this case. Now, as far as the solution is concerned, it is exactly the same. The equations are concerned, it is exactly the same. Only thing is now since these EI, these values are not same for different members. Now, these values are not same. These are different for different members. These are different for different members, and we need to, in the same equation, procedure is exactly same. We need to consider one hinge here and another hinge here, because for this structure it is the static indeterminacy is 2. We need to introduce two redundant forces, and the redundant forces in this case is moment at B and moment at C, and means that means the primary structure will be the same structure, but with two internal hinges at B and C. So, we actually release the rotational constraint. So, then apply three moment equation at B, and then apply three moment equation at C. When you apply three moment equation at B, consider span ABC, and when you apply three moment equation at C, again consider span BCD. Moment at A and moment at we know that moment at A is equal to moment at D, and that is equal to 0. So, only unknown will be moment at B and moment at C. The entire process is exactly the same that we have done in the previous class, but the only difference here is in the previous class, since all EI were constant, same value, in the equation there was no we did not write the equation in terms of EI, but since it is now it is different. So, when we consider span, say we consider span ABC, then this case it becomes 2 EI. It becomes 2 EI, then in this case it becomes 2 EI, and it becomes EI, and it becomes EI, and then again it becomes 2 EI, and it becomes EI. All other values LAB, AB, XB, BC, XB, they are all same, because they are the moment due to the primary moment in the primary structure due to the external load. So, now then we get two equations in terms of MB and MC, solve them and get the values of MB and MC. Once we know the redundant forces, then rest is just to draw the free body diagram of different parts and apply the equilibrium conditions. Okay. Now, Similarly, if we have to do it for this was for 3 moment equation at B. Now, if you have to do it for BC, then if you have to do it for BC, then suppose this is BC, this is BC, this is for BC, this is for BC, and BC, this becomes CD, this becomes CD, and this becomes CD. Again this become for BC, and this become for CD, okay, CD, and then this become MC becomes MD, and this becomes MB, okay, and this becomes MC. Then the difference will be this is EI and this is EI. This is half EI, and again this is half EI, this is half EI, and this is EI, and this is half EI. And again rest of the process is exactly the same. You apply the equations, solve the equations, and then get the unknown, and then finally draw the free body diagram of different parts and apply the apply the equilibrium condition to get the unknown. Okay. So, this is the procedure when the flexural rigidity of different members are different. Okay. Now, next take another example. So, this was the example for this is interesting. This was the deformed shape for when all the rigidity, flexural rigidity of all the members were same. Now, if they are different, then this is the deflected shape. Now, both the deflected shapes are scaled to a same value, they are scaled by same factor. Now, then we can easily see here when we increase the flexural rigidity of member AB, means it is now the deformation of the member, the stiffness is now more, so naturally the deformation in that member will be less. On the other hand, the member CD, the stiffness of this member CD was reduced, and then therefore the deformation we can expect more deformation in member CD, and which is evident from this deformed profile, that this deformation is more and this deformation is less compared to this part. Okay. Now, take another example. Okay. Take another example. This is again almost similar example, but instead of what we did is we removed the span AB and provided one fixed support here, at A. Okay. Now, what is the static indeterminacy of this problem? Again, the static indeterminacy is if we remove B and C, then also it becomes a cantilever beam, so which is determinate and stable. The presence of support at B and C make the structure indeterminate. So, in this case the static indeterminacy NS is equal to 2. So, we expect 2 redundant forces. Okay. Now, next is now this is you see this is the beam. Now, how to treat when your support is fixed support. Now, what it means, suppose what it means fixed support means the displacement, it has all degrees of freedom are constrained, right. Now, all degrees of freedom are constraint means what happens, if we extend, suppose this is the actual length of the beam, AC is the actual length of the beam, and if we assume a fictitious beam, say fictitious length of the imaginary length of the beam, which is say it is A dash, A dash could be of any length. Okay. Now, what happens, since at point A the displacement and the rotation all are constrained there, all degrees of freedoms are restricted, okay, are constrained. Now, we can assume that if we extend the beam up to an imaginary length A dash, that could be any value, then the rigidity of this beam, there is no deformation in the beam. There is no deformation in the beam. Now, if we consider the beam ABC, then the deformed shape, probably the deformed shape of the beam, if this is the ABC, then deformed shape of the beam probably this is something like this and then something like this, okay, for some loading condition. Now, if it is extended to some length, say it is a dash, then it means that up to it is up to a dash to a, there is no deformation, and then from then that deformed shape becomes like this. So, means a dash a is a beam length, an imaginary beam length, but which has infinite flexural rigidity, Therefore, since it has infinite rigidity, so there is no deformation in the member in this fictitious length a dash. Okay. So, now if it is, then take this beam member of the beam ABC, actual beam is ABC. Now, beyond this fixed support, assume there is an fictitious length which is a dash, and then this fixed support, if you remove by a roller support like this, and make this is a dash, and make this in this rigidity of flexural rigidity of the member a dash a is infinite, then this is, and these idealization of this beam, they are similar. Okay, their behavior will be similar. So, what we do is, instead of considering this beam, we consider this beam because they are similar. Okay. Now, if we do that, then what happens? So, the equation, this is the equation, the same equation, but important part is, now we need to apply the 3 moment equation first at point A, and then apply 3 moment equation at point B. Okay. Now, when we apply 3 moment equation at point A, then we need to consider this span A dash A and A B. Irrespective of the length of A dash, there is no length written here. What is important here is, now their flexural rigidity is infinite. So, if the flexural rigidity is infinite, then the corresponding contribution, this part becomes infinite, So, therefore, their corresponding contribution, since it is 1 by EI term, their corresponding contribution become 0. So, what you get is, if you apply 3 moment equation at point A, so contribution from this part becomes 0, and then what you have a relation between between bending moment at A and bending moment at B. Then you consider the 3 moment equation at B, and then MC is equal to 0 here, because it is roller support. Then again, by considering 3 moment equation at B, you can get a relation between moment at A and moment at B. So, you have 2 equations which give you relation between moment at A and moment of B, and then if you solve those 2 equations, we can get what is the value of moment, what is moment MA, what is MA, and what is MB. We can get this. Okay. Now, this step is, this length is immaterial, because you see here, what irrespective of the length, if this is A dash A, always we have 1 by EI term, So, irrespective of the value of this length, since it is this EI term is infinite, this contribution for this support A dash, for A dash A, this span, this contribution will become 0. Okay. So, this is how you can idealize a fixed support when you apply 3 moment equation. Okay. Now, next is, if we see the deformed shape of this is the deformed shape. Okay. The deformation between A dash and A is 0, because it has infinite rigidity. Okay. Again, the deformation is scaled here. So, this is how the deflected shape of this beam look like. You can solve this applying the 3 moment equation and get the solution. I am not giving you the solution here, I am just discussing how you can solve it. Okay, there are similar examples given in the book. You can go through those examples and practice those examples. Okay, but the concept behind behind applying three moment equation for this kind of problem is this. Okay, now. So far what we have done is we apply three moment equation to a problem where it is mainly subjected to the some external loading, either in the form of distributed forces or concentrated forces or moments. Okay. Now, as I say, the external agitation may be given to the structure by allowing a support to move certain distance, so the support may settle for some reason, and because of the settlement of the support, the structures instead of, I mean, in spite of any presence of any external loading, the structure may be some stresses may induce in the structure, and correspondingly moments and the stress resultants, moments and shear also we can have in the structure. Now, this is one example, the same example like the previous one, but in this case, in addition to the externally applied load, what we have is the support B settles below by 10 mm. The support B settles below by 10 mm. So, if it is if the support B is settled below by 10 mm, and if the point B goes to B dash, and this distance is delta B, and this delta B is 10 mm. So, this delta B, so this is equal to delta B. Delta B is equal to 10 mm. Okay. Now, if you recall, this is the general expression. In the previous example, we did not consider this, we did not write this part because there was no support settlement in the previous example. So, these values of delta were 0, but since in this case these values are not 0, we need to consider this part as well. Now, this is the general expression. Now, up to this example, up to this part is exactly same as before. Okay. Now, this part is due to the settlement of the support. Okay. Now, so this part will if we consider only this part, this part will give you the moments generated in the structure due to the external load, and then this part this additional part will give you the additional moment generated in the structure due to the support settlement. Okay. Now, what is delta BA? Delta BA is equal to delta B minus delta A is the relative displacement between point B and point A, and similarly delta BC is equal to relative displacement between point B and point C, and we know that delta B is equal to this is delta B. In this case, we know delta B is equal to 10 mm, but delta B is equal to 10 mm, and delta A and delta C is equal to 0. So, when we apply three moment equation at B, delta A and delta C is equal to 0, we can calculate correspondingly what is delta B and BC, and use that in this equation, get the expression, get an equation for MB and MC, and then apply three moment equation at point C. But in this case, again delta B is 10 mm, but delta C and delta D is equal to 0. Again we get an equation for MB and MC, and then by solving those two equations, we finally get what is the values of MB and MC. And once we have MB and MC, rest of the thing is very straightforward. It is same as any statically determinate structure. Okay. Now, if you have to see the deflected shape of this beam, the deflected shape look like this. So, you can see here in this example how this support settles below. The movement of this support can be easily seen. You see, the moment of this support can be seen here. This moment of this support can be seen here. Okay. Now, this is the application of okay. So, these are some applications of three moment equations for continuous beam. As I said, we actually in this class we actually analyze just one example, and rest of the examples are in some way slight modification of the first example. Again, the idea has not been to show you how to solve, how to show you the different steps, because that we have already discussed. The idea is if you come across a different kinds of problem, then the same three moment equation, the general three moment equation, how that three moment equation can be used for different conditions. Okay, so the concept will be clear when you actually practice some examples. That you can take any book on structural analysis and please do some examples to make yourself comfortable with the concept of three moment equation. Okay, so what we do in the next class we'll use the method of consistent deformation. This is also a method of consistent deformation, but in a different form, as we discussed. The three moment equation is also the premise is method of consistent deformation. Now what we do next is we'll apply method of consistent deformation next class to indeterminate beams, for solving beams which are indeterminate. Okay, see you in the next class. Thank you.